let's move on to the industrial production of activated carbons. So you know what are activated carbons? These are porous carbon structures. They have a very good absorbance because of certain physical and chemical activation process, and of course because of their pore network, because they offer a very high surface area. Okay, so I told you that these are the carbon materials which are used for making, for example, water filtration columns in a number of air purifiers, water purifiers, and so on. How do we make these structures? That is actually not too complicated. So you can, for example, take some shape of activated carbon. You can take granulated activated carbon, you can take the powder, you can also take larger particles or cylindrical particles, all kinds of shapes, and then you can pack them into a column depending upon your requirement, depending upon what kind of what kind of impurities are you planning to trap. You can also activate these carbons in different ways. You can also use impregnated activated carbons. You can also here and there combine these columns with other, for example, electrochemical reactions. So with all of these things, the physical manufacturing process of a column, water filtration column, for example, would just be to pack a column and have certain filters and sieves, so that your water, before going inside the column, it gets primary filtration done, and also when it comes out of the filter, then it it does not contain any carbon in it. You need to make sure. So this is basically it. Okay, however, what is more important for us is to how to make these granular or activated carbons themselves. So what you buy in the market, these cylinders that you see, so how do you manufacture them? So that is what we are going to learn. This is what I call the industrial manufacturing of activated carbon, not using activated carbon but of the carbon itself. Okay, now so first of all, when we make these any kind of carbon, we need to know what are the suitable precursors for it. So as I have mentioned multiple times, that activated carbons are derived from natural polymers in most cases. So for example, wood, which is a lignocellulosic material. Lignocellulosic means the structure itself is made of cellulose, but it also contains a lot of lignins. Lignin also is a range of compounds which you find, these oily compounds, and whatever other than cellulose, you practically, this is the primary material that you have in the wood and natural materials, agricultural waste, and so basically plant materials. Okay. So lignocellulosic materials are the primary source of activated carbon. Now you can also use, for example, certain types of coals. So if you remember, we use needle coke for making graphite. We also use certain other types of cokes for making glass-like carbons or other non-graphitizing carbons. So now in the case of activated or char-like carbons, what you could also use is are the certain types of coals, not coke, coal. So coals are these relatively porous structures. Now, why do we find all these different why do all these different petrochemical precursors give you different types of carbons? Well, they are formed by different precursors. So when you, if you look at the history or how they were formed, then all of them were ultimately at some point formed by different types of precursors. Whatever was the result of conversion of natural wood-like polymers may have converted over time into coal. Now, coals are also of different purities, different qualities. In fact, in different parts of the world, you find different types of coals. Some of them, for example, certain types of bituminous coals and also brown coals, these are also used as precursors for making activated carbons. Okay. Now, peat is also one more. So, peat is something which is sort of organic material which has partially converted into carbon but not completely yet. So peat is also, so all of these materials are basically high carbon containing natural materials. That is what you use as precursors for making activated carbons. Okay. Now you can also utilize certain cokes which do go through softening. So after heat treatment, but if you pre-oxidize them at 150, in this range 150 to 350 degrees, then you may be able to prevent this softening to some extent. So these are also in although rarely they are used, but they can also be used for the formation of activated carbon. There are two main strategies, so to say. So if you think about the pellets or cylinders of activated carbon, either you can make the pellets before their carbonization itself, or you can make it afterwards. So what do you think is better? If you think about the graphite related manufacturing or glass-like carbon, we are always providing the shape before the final carbonization step. Because that is when once it is carbonized, then it becomes more difficult to give it a shape. So this is precisely what we also do in the case of activated carbon. So we usually give the shape beforehand, so you already take the precursor and make cylinders out of it, and then carbonize them. However, in certain cases, if you have a precursor that will not give you, or it's very difficult to to shape it, to form it, in that case, what you can also have is you can get the powder of activated carbon, and then afterwards you can use a binder and then provide a shape. Okay, so these strategies I have prepared sort of a chart. There you can see. So you take a polymer precursor. Now you can either, so what you want to do is you want to make pellets. So for making pellets, what do you need to do? Let's say I give you a lot of wood. Now first you need to crush it. You need to make sure that you have, basically you'll have to dry it first and then crush it and make uniform sort of particles. Okay, you may also need to do sieving. Because if you do the crushing of materials such as wood, or sometimes the seeds of the stones, these are also precursors for making activated carbons. In fact, in India, you often use coconut shell for making activated carbon, which actually gives you very good quality activated carbon. So what you would do is you do crushing and then also sieving to remove like really big particles and to sort of make the size to some extent uniform. Now you can either do crushing and then further milling rather than sieving and removing the bigger particles. You want to make sure that all the particles are utilized. So in that case, for bigger particles, you might do milling. So these kind of processes you will do to reduce the particle size. Or if you want to, so you remember that in the case of chemical activation of carbons, what we do, we pre-treat them. So in the case of physical activation, we don't, but in the case of chemical activation, you would pre-treat your precursor. So the pre-treatment already degrades to some extent your cellulose, which makes it easier to shape it. So these are the three pathways you will use in the beginning. Okay, now let's talk about the third one, where we do the crushing and milling. So we have basically a powder of your precursor material. Now what you will do is, here at this stage already, you will mix it with a binder. Now this binder again can be resin. In most cases, binders have some sort of resins, which may not really give you char-like carbon, but you're using reasonably small quantities and you need certain binder to hold and to make pellets. You definitely need certain type of binder. So that is what you will do, and then you might use extrusion techniques. So extrusion is where we also use extrusion in the case of graphite related manufacturing, also for plastic materials. So plastic extrusion is a very common manufacturing technique. So you will take now this mixture of your cellulosic material and binder, and then you will perform the extrusion to give it whatever shape is desired, and if needed, then you will do drying or even cross-linking depending upon what kind of binder did you use. Okay. Now you perform the carbonization. So now either you perform the carbonization for these particles which are mixed and you use the binder and you made the cylinders, or you can directly, if you wanted powdered activated carbon, for example, after crushing and sieving what you had in the first strategy, you can already carbonize that. Or if you were doing the chemical activation, then the pre-treated material that you have, whether or not you made pellets out of it, you could then carbonize it. So after all of these steps, you will now perform your carbonization, and you know that this carbonization is not performed at as high temperatures as you would use for graphite. So relatively lower, like let's say around 1100 degrees centigrade carbonization. After this, so now you have a porous carbon material in whatever shape you wanted it. Now you perform the activation. So in the case of chemical activation, this activation process already sort of started when you did the impregnation, but now you will you will further do some physical activation using steam, for example, and this is your activation step. And Now, after the activation, depending upon, again, what kind of shapes do you want? Do you want to do sizing? Sizing typically means that you cut pieces of, so if I make a very long cylinder and I want to make small cylinders out of it, that would be sizing. So this you can perform. If you have powder, you can perform sieving again, because you remember that there will be some change in the size during this process of carbonization. It may not shrink as much as the other polymers shrink, other resins shrink, but some shrinkage will take place. Not just some shrinkage, but also because of all of this sort of harsh processing inside your furnace, you may end up losing. So some of your material will erode. So that some carbon particles will come out. Some of these cylinders may break, or so some material damage might happen. So you need to purify again. You need to sort your structures again. So you will perform sieving and sizing, these kind of operations. Or if you wanted a powdered carbon, then you will perform grinding, or in some cases screening. At the end, you will perform some conditioning. So this is like a finishing step. So you will perform certain conditioning and ensure that you have material with a good purity and uniformity. And then finally, you will have different types of activated carbons. You can have granulated, powdered, or pellets. So this is basically, the idea is that you will either perform the shaping before in the precursor itself, or you will have the material and then afterwards you will have a binder. Okay. Yeah. Now coming to, so in the next slide, I'm going to tell you how do we perform the activation step. So this is like the overall process you will use starting from the precursor, but now we are going to the step where we perform the activation of porous carbons. So the activation is performed in different types of furnaces. What you need is basically a furnace. For all the carbon related operations, what is very important is high temperature furnace, and these furnaces must have a controlled environment. Now even if you do want to supply air in certain cases, or you want to supply steam, or you want to supply an inert gas, or you want to supply a mixture of gases, in all cases what you need is a furnace which has a uniform, which has a very controlled environment. However, the size of these furnaces can vary. So you can actually have these really massive furnaces that actually have a capacity of several tons of material at the same time. So you have really massive furnaces for processing, for the industrial process of carbons. At the same time, if you're making a micro nano device, you will use a lab furnace where you have the tube diameter of, for example, just a couple of centimeters. So the size of the furnaces may vary, but the principle remains the same. Now, in metallurgy, you would read about several types of furnaces. Different materials, different elements, different ores are processed in a certain different type of process, because of that mainly depends on, number one, the byproducts that come out of it, or also the some of these byproducts can be corrosive, or they can be very harmful, or they can also sometimes be used as a primary material, as an initial material for some other chemical process. So depending upon these, you basically want to you change the shape and size of the furnace. Okay. Now for activated carbons, the production of activated carbon is typically done at a very large scale. So these the furnaces that I was talking about, the several tons of capacity, those are the kind of things you will potentially use for making large scale activated carbons. Okay, that is also the reason you have this material is relatively cheap. Now when you use these kind of massive furnaces, you may not be able to perform joule heating using coils, which you would do in a lab furnace. So you have a coil around your ceramic tube or quartz tube, and then that is what is performing the heating, providing the heat. But in the case of several meters long furnace, you will rather use fuel. You will just use petroleum fuel, and you will, using these hot gases, you will perform the heating. In this case, it's also not too difficult because the temperatures are not terribly high. So rotary kiln is the first type of furnace that I'm going to talk about. This is the one that is most commonly used for making the activated carbons, for activation of carbons. Okay, and there are two other types of furnaces or reactors that we are going to talk about. That is, one is the multiple hearth furnace, or the fluidized bed furnace, or you can also call it a reactor. Reactor is a word typically we use when we have certain chemical reactions going on. Here you can also just call it a furnace. Okay. So the first one, the rotary kiln. This is a very large tube-like structure, several meters long. So this is a metallic, typically made of cast iron tube, which you will also maybe make in separate parts and join them together. But this is a very large metallic tube where you have the steam and the hot gas. Hot gas here is the one that is produced by your fuel. Now you can also have carbon dioxide. You can also have other gases, whatever you require for your activation of that type of carbon. So you have a very big tube. But this is where you have the steam flowing or whatever gases you need. What you have is the starting material here, because now we are talking only about activation and not about the carbonization process. So starting material is your low purity carbon. Now low purity carbons produced by the charring process are simply called chars. You will also hear the term biochar, because often these materials are prepared by biological, like plant materials and so on. And in many cases nowadays, they are prepared by waste materials. In fact, even if I talk about coconut shell or any fruit, stones and so on, these are waste materials. So waste is, your waste can be a starting material or useful material for something else. It's just waste for us, but it can be used. Also agricultural and forestry waste of all kind can be used for making chars. And these chars now they are prepared at lower temperature, so they contain impurities. Now, however, they do contain porosity. So those are our starting materials. And now we put them in our tube. Now, one thing you will notice in this tube is that it's an inclined tube. It's not a perfectly horizontal tube. It's slightly inclined. And there's a reason for it. If you have the tube that is inclined, then the material can move along. Due to gravity, it will just move forwards. Okay. Now, as the name suggests, this is a rotary kiln. So this entire thing keeps on rotating. Your entire cylinder keeps rotating. So if you've seen cement, your concrete making, on a construction site, so you see these rotating, for mixing you use these rotational devices. So this is also something that the entire thing rotates, so that your material, your char inside, that can keep on rotating. Okay. What else do you have here? I said that the temperature is, okay, you have fuel, you have hot gases, but what you do is you are often putting your source of heat on the other side, opposite side of the feed. Why are you doing that? So that the temperature increases this way. The gases flow this way. So when the temperature, you can see the arrow here, the temperature as you go like this, so the more you go towards the end of the furnace, the temperature increases, because the heat source is at the end of the furnace. Okay, why? Again, so that your material slowly heats up. It does not immediately experience a very high temperature. It gradually experiences a higher temperature. And the impurities are gradually removed. The byproducts, so you can have tar-like impurities. You can also have you can have other things. You also want to make sure that you impregnate steam into it. So initial stages will remove your impurities, and at some point you will also get the material impregnated with superheated steam. So the temperature is increasing along the length of the furnace. Okay. Now, so at the end, now you also have the material moving due to gravity, and at the end, your entire, whatever is the processed activated carbon that you will collect. So this here, I have drawn only a very basic schematic. Of course, this is not how an industrial plant would look like. These are, as I mentioned, these are massive structures. Then they will have a lot of different seals. You will have gas outlets. You may have multiple gas outlets. You will also have some steam injection, gas injection. So inlets and outlets of all sorts. You will have different valves, different seals, different. Also, these two big structures. They are like tires around. They're not rubber tires, but these are called tires. So these are ring-like structures around your furnace or kiln. You can even move this entire thing. So this is the basic diagram. The idea you can understand now. Why are we doing all of this? There must be some advantage of this kind of design, right? Why are we not using just a standard furnace? We are using this tube-like furnace because, okay, number one, in all tube-like furnaces, all the byproducts can be relatively easily removed. But here, the scale of manufacturing is so large that our goal is also to make sure that all the particles that we have, all the char particles that we have inside, whatever is the particle size, we want to make sure that all of them experience as much heat as possible. All of them also come in contact with the steam for as long as possible. This duration of your solid material coming in contact with the gases, this time is known as the residence time. So for how long does it experience the whatever is the gas around it? Okay, so you want to increase the residence time, and you want to also make sure that all the surfaces of your particles experience some heat. Okay, so if you keep on rotating them, then you can see that there is then you always each surface has the probability of coming in contact for a long enough duration, coming in contact with the steam or other gases. Also, this will lead to the heat transfer between the particles. So heat transfer is not just between the wall of the furnace and your particles, whatever the particle bed on that surface, but now your heat transfer is also between the particles. So to ensure all of these things, that is how these are some of the advantages of this design. Okay. Yeah, and of course one more advantage is that you don't really need to push the particles, so you don't need to remove them because of their weight, because as they keep getting processed, they will because of the inclination, they will by themselves they will come towards the outlet. Okay. Yeah, and one more advantage of this, because these are very large tubes, so you can control the temperature gradient very well, because they are really massive. In fact, you may have multiple burners to heat your entire structure, so you can have a good thermal gradient, which means again your particle is experiencing slow increase in the temperature, and that's why the process is more controlled. So these are the advantages. Now, if you have to decide the rate of production, then what are the things there? Number one, how fast you rotate your kiln. Number two, what is the angle at which your kiln is tilted? Because that's how, that will determine how fast your particles move and they come out. Of course, depending upon the rate of the feed, how much char you're feeding in. So that would also how much activated carbon you're taking out. So feed in, mass out. That will determine the production speed, and of course also other factors such as the steam injection, because that would determine the residence time. Sometimes you want to increase the residence time, sometimes you want to decrease, depending upon what kind of steam. Is it superheated steam? For how long do you, and also it depends on the particle size and so on. So all of these things will determine the rate of your production. Okay, now yeah, as I mentioned already, that they have these furnaces have several tons capacity. Sometimes in certain cases you may also use high temperature rotary kilns, so the temperatures can go up to 2000 Kelvin in some cases. Okay, now the often when you are operating any such plant or chemical reactor of any kind, not just for activated carbon, you will first perform certain simulations. So you want to understand how your entire setup is going to function, and then accordingly you will decide on the process parameters or the feed rate and so on. Okay, so typically whenever you want to model something, if I say that you need to model or simulate the operation of a certain rotary kiln, what you need to take care of is number one, the mass balance. So mass, you need to make sure the mass in, mass out, not just the char and activated carbon, but also the mass of the steam, also how much solid is getting converted into vapor, how much vapor is converting into liquid, and so on. So you need to perform you need to take care of, or you need to understand all sorts of mass balance. You need to also understand the energy balance. And of course, that is closely related to your heat transfer. So all sorts of heat transfer, whether it is between the walls, it is between the inner wall, outer wall. From outer wall, what is the heat that is being released into the environment? And all sorts of, whether it is convective heat, whether it is radiative heat, you need to factor in all of these things, and then maybe come up with some differential equations, and then this is how you model your system, and then you perform the simulations, and then you figure out what are the parameters that are required for your process. The next type of furnace that is used in the case of activated carbon manufacturing is known as the multiple hearth furnace. So hearth is basically these furnaces that are made of bricks, more like this fireplace kind of furnace. So you have basically refractory material. Okay, so this is a schematic diagram of these hearth furnaces. Now the names itself says multiple hearth furnace. So here I have shown these 8 stages. You can have multiple stages, you can have less, you can have more. The idea here is that you have these multiple hearth furnaces connected. This is a vertical system. And you have various heating zones. You can have various cooling zones also, and you can also have steam injection or whatever is your gas injection also at multiple stages. So what do we have here? We have this one shaft you can see in the center. This shaft is rotating. Now you have these disc-like structures. So this is a cross section here, you see disc-like structure, and you pour your feed from the top, your char. Now it goes, let's say, on stage 1, and then you have what is known as rabble arm. Rabble arm are these structures which are made for sort of rotating or spreading your the material. So they are made for rotation. So that now the material is rotated on the furnace number 1. After that it goes to number 2, after that it goes to number 3, and so on. And then again different processes are taking place at different stages. So what is the difference? In the rotary kiln you had sort of a continuous operation, but here you don't have continuation of heat. You have these well-defined stages, and the number of stages you can determine. Okay, now what happens at these different stages? Basically, on the first stage, if you have sort of some moisture in your char, so first some drying will take place. Second stage, there will be some pyrolysis. You may so pyrolysis also, if you take the precursor and you want to make the coal, for that also these kind of furnaces can be used. Okay, but in the case of when you want to convert them into when you want to just perform the activation, in that case pyrolysis may take place if you have some organic material left over in it. So for example, for very low purity chars, so there may be some pyrolysis, some combustion also, if you want to burn away the undesired impurities. Okay, so that will take place. Now you will also have then some fixed carbon burn. So fixed carbon is the carbon that you don't want to lose. Okay, now but some gasification burning will take place as well. That is what happens at the time of your activation. You know that you do lose some carbon mass during the activation. Okay, now also then if whenever there is certain burning, oxygen is present and you have some burning, in that case you will get some ash. Ash is actually a big problem in furnaces. In all industrial processes, it is the ash formation, especially in the case of carbonization, pyrolysis plants, waste treatment plants. It's the ash formation, ash content, that's a big problem. What we would like to have is, so there is certain type of ash which is extremely light and it flies. So it basically goes on top. And then there is certain type of ash which is relatively heavy, or the particle size is large enough, or the process is done in such a way that the ash can be collected in the bottom. So here in this particular furnace, you can see this is a vertical furnace. So whatever products are being generated, they are coming to the bottom. So the ash can also be collected in the bottom, which is a good thing. This type of furnace does not generate much fly ash. Okay, so this is also an advantage of this type of furnace. So again, why would you choose a rotary kiln, or why would you choose this? That would also depend on your precursor, whatever type of char you have, whether you have a already high purity char, or you're using certain type of coals and trying to activate them, or you're just using a very low purity char from, for example, something that is generated from waste. So depending upon that, because that will also determine how much ash content you will have, so how do you want to collect it and so on. So based on these things, you can also choose this type of furnace. So these are some other things that I have already told you. Rabble arms are rotating your material. Hot gases. So here also you're performing the heating by using simple fuels. So hydrocarbon fuels. So the hot gases, then these hot gases are flowing upwards. So here also you have a counter flow of heat, similar to rotary kiln. So you have heat from one side and heat from the other side. Again, to ensure the same thing, that the material slowly goes towards the higher temperature. Okay. And then of course again you will have several injections where you can inject your steam or carbon dioxide. Also you will have some other outlets, some gas exhaust outlet. This gas exhaust, by the way, it's also known as flue gas, the exhaust gases. Okay, now the problem with this kind of furnace is that compared to the rotary kiln, you have relatively lower residence time, and that is why sometimes your the carbon can be of relatively inferior quality. But also you can use these kind of furnaces. In fact, they are rather used for reuse of the activated carbon. So these all activated carbons can also be reused. So once, for example, in your house water purification column, once it gets sort of saturated with the impurities, then what you can do is you can just remove the carbon. Again, you can take the carbon out of the furnace of your column and then reheat it. So for these kind of recycling purposes, reheating purposes, these kind of furnaces are more commonly used. Okay, what will be the optimization parameter for this kind of furnace? Number of hertz. So how many stages do you want? That is very important. What type of operations do you perform? If you have too much moisture, or if you have, how do you want to gradually increase the temperature also? So the number of hertz is important. Then of course, because as I said, these rabble arms are rotating your material. So that kind of the speed of that rotation, because that would decide your residence time. Of course, the temperature at various stages and feed rate, feed in, feed out. All of these things are your optimization parameters for these kind of furnaces. Okay, so the third one that we will quickly discuss is the fluidized bed type furnace. Okay, fluidized bed. The concept of what is a fluidized bed? What you so it suggests that there is certain fluid in it, but it's not just a fluid. What you have is you also have solid particles mixed inside that fluid. So they are like suspended solid particles in a fluid. With the fluid can, by the way, also be a gas. So what will happen is you make this mixture in such a way, and also you create so much turbulence in that fluid, that basically your entire mixture of solid particles in the fluid, the entire mixture behaves like one single fluid. So that is the idea of any fluidized bed reactor. Now this is you can have different chemical reactions also. These reactors are used more for different other chemical reactions, because there you can have, for example, one matrix, and then you have the particles. You want these particles to react with the matrix, or you want to even perform certain types of coating on top of your particles. In that case, this is perfect, right? Because if your particles are suspended inside a fluid, then each surface all the time is coming in contact with the fluid. So if you want to perform certain reaction with the fluid, then that is perfect. In our case, you can have steam and you can have the char particles suspended in it. And now if this entire material, this entire mixture behaves like one single fluid, then we can control their flow rate. Then basically whatever we do to the fluid, that is how we can treat this entire mixture, which is actually what you can also call, it's a heterogeneous fluid. However, we sort of, when we think of this heterogeneous fluid, we do consider one single bulk density. So we don't say that the density of particle is this and the density of the fluid is this. We just think of this entire mixture as one single fluid, and then we consider the bulk density for it. And that's how, when that is what you would use if you want to model it, or if you want to calculate any properties, any parameters, or simulate anything. Okay. Now, this, of course, the advantage. So the principle, the operation principle is simple. You see that in the figure, you see that you have the char in, you have activated carbon out. There is certain fuel, there is certain gas and steam injection, and the flue gas, the exhaust gas can go out from somewhere. So this is the idea is that you have this mixture of fluid and solid, and there is always almost a continuous turbulence created. So then you are at all times the particles are suspended in that fluid. Okay. So now here you can imagine that because the reaction is happening all the time, you actually need smaller residence times. In fact, if you end up having a very long residence time, you know that you may end up losing your carbon. So the optimization of residence time here becomes important, because the reaction is relatively quick, because all the surfaces are always, so this is like a very, what should I say, very, not harsh, but it's a constant reaction. So that is why it is important that you ensure that you have the not very long residence times. Okay. Yeah. So also what will happen is, because your steam or hot gas, whatever gas, is always it is around that your your char particle all the time with very high velocities. So heat transfer is also relatively fast. So because of all these factors, you need to make sure that you don't leave the carbon for too long inside the furnace, or you may end up losing the carbon mass, the fixed carbon mass. Okay. Yeah. So this reaction can also cause mechanical damage because of the velocity of the fluid. So you may, because these char-like particles, activated carbons, they are not mechanically too strong, at least as compared to other carbon materials. So you may also get some erosion from the surface. These are the things that you will need to optimize. Okay. Now, of course, why will you use, in which type of carbons you will activated carbon, you will use it rather for the powder, for two reasons. One, that the damage to the powder surface is less. If you have bigger particles, you may end up crushing them. And also because the powder is light, so the particles are very light, so it is easier for them to have them in the fluidized bed. Okay. Okay. Now, yeah, these are also used for reusing or reheating the activated carbon. The good thing, in fact, the one big advantage of activated carbons is that you can always reuse them. So whenever your the activation absorption is exhausted, your material is saturated with it, in that case you can just heat it again, wash it again with several chemicals, and you again have your activated carbon ready. So this is also one reason that this is a very important industrial material. Okay, if you want to read further on activated carbon, this is in itself a very vast field of research. This is one book that I suggest. There are also several papers, review articles that you can read. This activated carbon is also very important for waste treatment, and a lot of carbonization that takes. So if you carbonize waste polymers, often you end up getting either a mixed type of carbon, or you get porous carbon. You don't get good quality graphite or glass-like carbon, of course, from the waste. So in that case, conversion of char into activated carbon, and then utilizing these activated carbons for different processes, that is very important.